وہ سر زیڈ ٹرانسفارم کی اسائنمنٹ آپ نے دی ہے یہاں پہ؟
وہ میں آپ کو بھیج دوں گا انشاءاللہ. کوئز ہم نیکسٹ ویک کر لیتے ہیں پھر, ٹھیک ہے؟
نیکسٹ ویک وینسڈے.
اچھا صحیح ہے. اور کچھ رائٹ یہ میں کروں یا نہیں آپ لوگوں کی بارگیننگ ریکارڈ چلے یہ پروف ہو جائے گا نا کیا ڈیٹ پہ آئی تھی. جی جی
فوٹونکس والی بھی ٹرپ جا رہی ہے, اس کے ساتھ ماڈلنگ جا سکتی ہے.
سر ہم کیا کہہ رہے ہیں,
فوٹونکس والے جا رہے ہیں. آپ لوگ گئے نہیں تھے کوئی آپ نے؟
سر وہ تو ہم ساتھ گئے تھے 20
نہیں وہ بھی اور آئیں گے, وزٹس آئیں گے. ایکچولی وہ دے ہیو ٹو ایڈجسٹ اکارڈنگ ٹو جو وہاں یوتھ ہاسٹل میں جو جگہ ہے اور ٹرانسپورٹ کے نا اس لحاظ سے وہ کر رہے ہیں. تو فائنل ایئر کے بھی سیمی کے بھی جا رہے ہیں اور فوٹونکس کے بھی جا رہے ہیں. اور مطلب اس بیچ میں 36 لوگ ہیں.
سر ادھر بھی مطلب ماڈلنگ کے لیے جا رہے ہیں.
ماڈلنگ کے اس میں نہیں ہے ان کا, شاید الگ سے ہو جائے گا. ہاں کر لیں گے. اچھا تو آپ چلے اس کو ہم دیکھ لیں گے. ابھی تو ہے یہ تھوڑا شارٹ نوٹس پہ تھا وزٹ. ابھی میں نے گول دیا ہوا جو ہمارا الومنا انڈسٹری یونٹ ہے 1 وزٹ پر منتھ, رائٹ؟ سب کے لیے نہیں لیکن ڈفرینٹ سب گروپس یا بیچز جو ہمارے ہیں. تو اگر یہ ہم انشاءاللہ دس از دا 3rd month دیٹ وی آر اچیونگ آور ٹارگیٹ. بلکہ آپ نے انسٹرکٹر کو شکایت کر کے جو زیادہ اچیو ہو گیا شاید آپ پہلے بھی گئے تھے اور آپ پھر جا رہے. تو انشاءاللہ امیجن کہ اگر ہم یہ اراؤنڈ 9 months a year, 3 تو آپ سمر پہ ہوتے ہیں تو کر سکیں تو کافی آپ کا سال میں کافی وزٹس انشاءاللہ ہو جائیں گے, رائٹ؟ پھر انہیں بہت سی ڈیٹیلز ہیں, وی کین ناٹ آلویز ارینج ایوری تھنگ, لیکن کمپیئر دس ٹو واٹ یو ہیڈ اوور دا لاسٹ few years, so I think it would be a huge gain, improvement, right? انشاءاللہ اس کو ہم کوئی ورکیبل پلانس بنا رہے ہیں. باقی محل لاہور میں آپ لوگوں کو زیادہ انٹرسٹ ہے کیونکہ ادھر سے جانا ہو تو آپ لوگوں کو کالیں کر کے بلانا پڑتا ہے, رائٹ؟ تو کیا لاہور نہیں دیکھا ہوگا؟ نہیں دیکھا چلے اس سے پہلے کہ سارا کچھ ہم کچھ اور ہی ریکارڈ کرتے ہیں, رائٹ؟ سو رائٹ, this is our lecture after the mids where we have already finished Z transform, right? We had around 5 lectures on that. What was the final lecture about on Z transform? So yaad hai? Something we did regarding modeling a system from history of its inputs and outputs. Remember? Yeah. So we said, let's say I have history of inputs and outputs. So when I give an, let's say, input of x n minus 1, I got an output of y n minus 1. Yeah. And when I gave an input before that, the output was yn minus 2 and so on. So we have some history of inputs and outputs, yeah? And we want to say, okay, now at this point, if I give input xn to the system, what will the output be, right? And we said that for LTI systems, you can do that. Write the output as a linear combination of past inputs and outputs. Okay, so to answer this question for a LTI system, if you have some history of inputs and outputs, you can tell me what will be the output now at y time n. So basically it was, we say, let's say it's a naught xn plus a1 xn minus 1 plus a2 xn minus 2, so on. If you have, say, n points, then xn minus n. So this, what is this? Mathematically a linear combination of the past inputs, right, including the current one. So abhi gya, yeah. Then With that, we wanted to include linear combination of the past outputs. How did it behave with each of these? ये training हो रही है ना system की ना, right? So how did this, when you sent it xn minus 2, what did it do, right? So we added that with a negative because we will eventually want to send it there, so it's no big deal. But if we do that, then you have b1 y n minus 1 minus b2 y n minus 2 and so on till vn y n minus n. This is also a linear combination. Okay, so linear combination of the past inputs and outputs together. ये क्या दे रहा है आपको? Current output. अब क्या उसकी state होगी? Right? What will be the position, response, energy, whatever जो आप measure कर रहे हो system का होगा. Then what did we do to simplify this? What was this equation called in mathematics? This kind of equation? Difference equation. This is the discrete time counterpart of differential equations. Yeah. Difference equation को more elegantly firstly लिखने के लिए, that's not the only reason by the solve भी, it gets solved much easier. I showed you an example last time. What did we use? Z transform. And what was it in the Z transform that helped us? It was that if xn has a Z transform xz, then xn minus m has Z transform Z inverse, sorry, Z minus m x z. Yeah. What I skipped here, there are some initial conditions depending on the order of this. Okay. So x, small x at -1, small x at -2 and so on, the initial conditions. But you can see those in the table. We often skip them to write this in a more elegant or simpler notation, but they are there. Okay. But if we go by this whole thing reduces to, firstly you get the Z transform of course, but also the whole thing reduces to something very elegant. Yeah. If I bring the outputs to this side, right, and leave the inputs here, so what we ended up, if you remember, was yz times this thing, this whole thing, we call that a pz, right? And then you had xz times the a naught z minus 0 a1 z raised to -1, a polynomial in z, right? That polynomial in z we called it q, p over q karna, so probably we call this q. Yeah. And this was pz, right? Then what was the output? Output was simply in the z domain, it was pz divided by qz times xz, right? So in the z domain, it is simply the transfer function multiplied by the inputs z transform. So this was a very quick review of what we did last time. You hopefully have gone through some of it, but please go through that again. And this form, we will come back to it. Okay, in Laplace and in Fourier, the concepts don't change much. What changes is you have Ps for Laplace, Pf or P omega for Fourier. That's about it. But now today is not about Z transform. Today is about translating what we have learned in the last maybe 15 lectures or 12 lectures on discrete time signals and systems, translating that to continuous. Okay. If you remember when I mentioned my plan of covering the course, what order did we go in? We did chapter 1, then what did we do? 3. What happened to chapter 2? It was continuous time. Then we went to chapter, after 3 we went to 5. What happened to 4? It's continuous. So 1 is a generic, chapter 1 is very general. So that was everything. 2 and 4 are for continuous time signals and systems. Okay. 3 and 5 are for discrete time signals and systems. Conceptually, 2 and 3 are counterparts of each other. Okay. 4 and 5 are counterparts of each other. Yeah. The reason I did the discrete time first was, what was the reason? I mentioned it before. Because it's easier to grasp because it doesn't involve integrals. Summations थी ना? Convolution में क्या थी? Summation था. It involves difference equations in summations, so it's easier to grasp a bit. But once you have grasped it, in one lecture, almost one or maybe next one also, in about 2 lectures, we will simply translate all of this into this, or map all of this onto this. And we can go really fast through it. You know why? Conceptually, कुछ फर्क पड़ना ही नहीं है उसमें. जो आपको समझ आ गया, if you understand what is an impulse, if you understand what is unit step, if you understand what is convolution, if you understand what is LTI, if you understand what's a transform, right, then you get everything in time domain, continuous time also, no big deal. So it's going to be pretty fast. We are going to go through chapter 2 and 4 important points really quickly, but not really in the order that they're covered, but more in terms of translation. So what I want you to keep in mind in this journey of ours, yeah, is these 3 things that are going to change for us. By now you are used to n, discrete time. It's just a notation, yeah, it doesn't really mean discrete times will be replaced by t. Okay, in chapter 1 you already saw continuous time, but then for all of the rest of the lectures we were sticking to this thing. Okay. Secondly, remember this guy, the everlasting exponential. What was z? Any complex number. This formed, what was it, an eigenfunction of LTI systems. If you send this as an input to an LTI system, it comes out the same. Yeah. So this will be replaced by the eigenfunctions of the continuous time LTI systems, which is this guy, EST. This is complex exponential in discrete time. This is complex exponential in time. And you're more familiar with this guy. Or you already know this. कौन सा फंक्शन है जिसका आप इंटीग्रल लें तो खुद आ जाता है? यही था ना? उसके अलावा कौन है? कोसाइन साइन, वो तो इसके अंदर होते हैं. रियल और कॉम्प्लेक्स पार्ट होते हैं ना इसके. So you already know that integral is a linear operator. So usme comes back, it's an eigenfunction. Right, so like z was any complex number, now s is going to be any complex number, and by convention we're just going to write this. आप इसको a plus j b भी कहते हैं, it's not a big deal, okay, but conventionally we write it s is a complex number. In discrete time, what was z? A complex number, a plus j b. So now it's replaced by EST. Yeah. और ये abruptly नहीं replace हुआ. We will see and you can test. For continuous time systems, it's this exponential which is the eigenfunction. It goes in and comes out the same with some scaling. Yeah. Okay. Third change. This guy, summation, replaced by integral. Okay. And of course difference, like this kind of thing, xn minus 1, let's say plus or minus xn, this kind of equation will be replaced by dxn. Yeah, but वो इसमें भी basically cover हो जाता है कि from summations and these you go to differential equations. So summation becomes integral, and really that's about it. Okay, यही है बस. बाकी I'm just going to complete the discussion just to have it done. Otherwise, it's really very much the same. इसमें more conceptual is this one only. N to T is convention. This is understandable. Summation becomes integral in continuous time. This is a bit interesting. In discrete time, the eigenfunction looks like this. Yes, a complex number raised to the time index n. In continuous time, the complex exponential or the eigenfunction of LTI looks like this. It's the the exponential e raised to s t. Okay. Right. So now let's do a side by side write up of what we need. Okay, our friend, the impulse. थोड़ी revision भी हो जाएगी, yeah? It will tell me how much you know by now. क्या है impulse की definition in discrete time? One at when this whole argument becomes 0. Yeah. Some of you still confuse this. You think that delta n minus 2 equals 1 when n is 0. It's not this. It's not saying that. Right? Uska pura argument, the whole thing inside, meaning n minus 2 should be 0, meaning n should be 2. Okay, ये जरा थोड़ा सा पेन में रखा करें इसके पैटर्न को. Right. So 0 otherwise. Yeah. What's the complex counterpart? We have already done this in chapter 1 briefly, but if you remember, I mentioned that delta is defined through two conditions. There is a delta t function in continuous time, the continuous time impulse, that has two conditions. If any function meets those two conditions, we say it's a continuous time impulse. What are those two conditions? Firstly, that it is 0 for t not equal to 0. First we say what happens at t not equal to 0. Okay. Then we say what happens at exactly t. We don't say that. What we do is we say delta t dt equals 1. Right. So we have done this in detail, but I'm just covering this here again for completion. Right. Second, delta n minus n x n. किसी को याद है ये क्या होता है? So x capital N, and to make sure that this function is only at capital N, we still keep this guy with us and we write it x capital N. Why? All the other values of x n don't matter, right? They will be zeroed by this product. Yeah. Okay. So what happens in continuous time? Equivalent to that. So let's say we have x, if we use tau, I guess, or capital T, okay, x t minus t phi t, sorry, not x, delta. This becomes delta t minus t phi t, okay, just like what you had before. Okay, so there are others, but I'll skip some and I'll come to this. Xn convolved with delta n. Anybody remembers? क्या था? HN. वो तो है अगर xn is delta n and then you're looking for the output. Identity. Delta n is identity of convolution, right? So
convolution
xn,
xn
right? 1 is identity of multiplication. X times 1 is x,
xn
right?
x.
So delta n is identity of convolution. So आपको करनी नहीं है convolution इसमें, करके देख भी सकते हैं, लेकिन it is simply xn. So same holds in time domain. xt is again xt. Okay, nothing new here conceptually. If you remember this one, we were able to write a given signal as a sum of shifted and scaled impulses. ये याद है? When we derived the convolution formula, we actually started somewhere over here. So what happens in continuous time? Something very similar. Xt can be written as a continuous sum, which is now an integral of scaled and shifted continuous time impulses. Again, याद है मैंने क्या कहा था? Summation replaced by integral, right? And then of course, I said n or something replaced by t, so that has to happen. Otherwise, it's very similar. Okay. Tau, yes, it's like this. Tau. Yeah? Okay. So, what about the output of an LTI system in continuous time? Let's see. If you send in this input, then the output, space. If there is a continuous time LTI system and you send it an input which is a linear linear combination of scaled and summed impulses, then the output is also a linear combination of those whatever you had originally. So this we did in detail for the discrete time. Yeah, now it holds. So if you send in, let's say, delta t and you get out ht, we call that the impulse response in continuous time. Now if the system happens to be LTI, what happens? If you scale it, this gets scaled. Yes. If you make linear combinations of this, you get linear combinations of ht. This is what happening. See, this whole thing I can call it xt, my input. Yeah. So delta was scaled by x tau, so h is also scaled by x tau. Delta was shifted by tau units, so is h. Deltas were summed up continuously, meaning integrated. The output is also integrated. This whole thing holds only when you are dealing with LTI. Again, I am rushing through this because we get this in great detail for discrete time. Yes, all I am doing now is replacing the summations with the integral. So what does this tell us about convolution in continuous time. What is the formula of convolution in continuous time? This is, there you have it. It is basically minus infinity to infinity x tau h t minus tau d tau, and we can write it as xt convolved with ht. Discrete time का याद है आपको? Convolution का formula. It was summation xn hn minus k, right? Or xk hn minus k, sorry, yeah. So same here, notice it's x tau h t minus tau. The only difference now is you have replaced the discrete time things with the continuous time things, yeah. Otherwise it's the same. So this is convolution basically, yeah. लेकिन किस में? Continuous time में, okay. And we have done convolution in great detail. हमने उसकी graphics भी देखे हैं सब कुछ. All those results still hold. They are the same. Okay. So nothing to repeat here. Even the properties. Remember we did the properties of convolution, right? They are very similar. कुछ उसमें नया नहीं है. So you can just take a look in your book, section 2.41 and 2.42, just to get an idea. Okay. So the properties of convolution that we did in detail, they are also the same. Now, if you remember, we characterized LTI systems through their impulse response, right? So let's see. In discrete time, let's say there is an LTI system. If there is a discrete time LTI system and it has impulse response Hn, yeah, what condition did Hn have to meet to be, for the system to be causal? Do you remember? Yeah, based on impulse response, not the basic definition. Yeah, is the general definition of causality.
Yes, sir.
Hn equals 0 for n less than 0. ज़्यादा है, ये हमने derive किया था पूरा, but I won't do it for them. Exact same thing holds for continuous time LTI. You have impulse response as ht, and it's the same, ht equals 0 for t less than 0. Okay, so if that holds, we say the system is causal. इसकी reason भी मैंने develop की थी for discrete time. Okay, it was easier there because there were summations, so I was able to expand it and show you what was happening. यहाँ थोड़ा सा आप discrete continuous में you could get scared. Okay, for discrete time, what was the condition on Hn for stability?
Unbounded, bounded input leads to bounded output.
Yeah, that's general, right? Now you have established that the system is LTI, and it has an impulse response Hn. From here, can you tell? Usually से आसान होता है, बताना ना. What was it? If you remember, it was that the absolute sum of this
Should be less than infinity.
should be finite, right? यही था ना? So sum of the absolute should be. तो फिर continuous में क्या हो जाएगा, आप कोई guess करें? यही हो
Same
जाएगा.
होगा.
Integral of the that's it, right? What are we saying? Area under the absolute of the impulse response should be finite. Yeah. So if I tell you that there is a system, LTI system, continuous time, whose impulse response is this, and this value is say 10 or something, is it stable or not?
Stable.
Stable है. You can see the area under the absolute है ही सारा positive, तो ये area बनता है. This, unless this is infinity, let's say this is 10 also or some value, then without calculating you can tell me that this is a stable system, right? Because the area under the absolute of the impulse response is finite. Yeah. Okay, so this was more about chapter 2, right? Mapping of chapter 3 to chapter 2. याद है इसमें हमें काफी lecture लगे थे इन सब में. One whole lecture dedicated to LTI, one whole lecture to convolution. Abhi just since the concept is same, there is nothing conceptually that I need to cover. You may need to cover because आपको पिछला भूल गया मुझे लगा. But yeah, if you go through your notes and right now we go to the frequency domain. याद है? For discrete time, what did we do after having done all of this? We went into frequency domain, Z transform, last 5 lectures. उसमें क्या crux क्या था basically? It was that gamma n or Z to n, let's say it goes in, you get a gamma, alpha gamma n outside. So this was dt LTI, and for continuous time, as I have already mentioned, we proved this also, by the way. Remember, convolution से हमने prove किया था, if gamma n is the input, then the output is again gamma n multiplied by some scalar, some scaling value. You can also prove this one. Okay, maybe we will do it, but you already have some idea of that. This is a for integrals. This is a eigenfunction. So where is it? Yeah, alpha est. This is continuous time LTI system. Okay. Now interestingly, just this basic statement from here to here, what transform did this lead to in discrete time? The Z transform. Yeah, frequency, but within that Laplace Z all for our frequency transform, right? But between that, in that it was Z transform. Now just the fact of going from here to here leads to a completely different or that's a bigger range of transforms or well-known transform, which is okay. That's it. Bagi properties, the way you solve even the inverse Laplace is very similar to inverse Z. What did we do in inverse Z? We applied, if you apply properties and table, then the properties of table and table of Laplace are very similar to this. Okay, and you don't even have to memorize them. If there is a question in the exams, I give the table. But you have to understand how they are used. Yes? What was the other way of inverse Z transform? Partial fraction, expansion. Same here. Okay, nothing new. Only in the partial fraction expansion thing you were dealing with Z, now you deal with S. There Z was a complex number, here S is going to be a complex number. So what is that foundation? Before that, let me expand for you what we mean by S. As I said, S is sigma plus J omega. What does that mean about EST then? It becomes E sigma T J omega T. Then this is EST, right? Agreed? What does this remind you of? We have looked at this function in detail, right? This is the complex sinusoid, which is could be growing. याद है हमने एक वो किया था उसकी different देखी थी realization. If sigma is positive, this is a growing complex exponential. Sigma is negative, it is a decaying complex exponential. If sigma is 0, this thing disappears and it becomes a perfect sinusoid, right? Jiska real part is cosine, the complex part is, imaginary part is sine, right? So we have done this in detail before. Right, so this thing leads to the Laplace transform, and the Laplace transform very simply comes in a way that is much familiar to you. What was Z transform, by the way? The bilateral Z transform. क्या definition थी? याद है इसे summation x n that was time domain times z minus n, remember ऐसे ही था. और for bilateral n was minus infinity to infinity. Yes, we allowed that for n. And then we had what related to this radius of region of convergence, the values of z for which this sum exists, it doesn't become infinite. So can you now guess what will be the Laplace transform of a continuous time signal? क्या लिखो यहाँ पे पहले इंटीग्रल आ गया. गुड. अगर ये भी हमने बायलैटरल लेना है तो ये माइनस इन्फिनिटी टू इन्फिनिटी हो जाएगा. व्हाट एल्स?
डेल्टा n.
Whatever notation we use for Laplace.
Yeah, what is that? अभी आपने इसका counterpart you told me. Counterpart of this you told me. What's the counterpart of this?
Delta t. Delta t.
No. अभी मैं काफी सारा repeat किया. Why is it here? It's the eigenfunction of discrete time systems. Yes. What's the eigenfunction of continuous time system? It was EST. ये माइनस के साथ है for a reason क्योंकि उल्टा है तो वो भी माइनस के साथ ही आता है. It doesn't affect. E minus st is also an eigenfunction. Okay, that's not an issue. और क्या रह गया? dt, right? Okay, continuous है तो these guys come together always, right? इधर जरूरत नहीं होती, वो इधर ही cover हो जाता है. n equal to minus infinity to infinity. Yeah? Right. So this was z transform, and this is Laplace transform. Okay, the continuous time counterpart of the z transform. And now yeah, it also has a region of convergence associated with it. What will that be? The values of s, e तो constant है ना, उसको तो लेंगे. The values of s for which this area is finite. That's it. Okay? The value of z for which this sum is finite was the region of convergence for z transform. Then the value of s for which this integral or the area under this whole thing is finite, we will call that the region of convergence of the Laplace transform. Okay. So इतनी इनमें similarity है कि you don't even have to memorize anything here. Okay. As long as you know integral and summation are counterparts, and these are counterparts in continuous and discrete time. Okay. So again remember there z was any complex number, here s is any complex number which may be restricted depending on convergence. Now I've written here properties and tables of the Laplace transform. Yeah, you know what I've written? Just 3 words. Similar to z transform. That's it. Just go. आप किताब में खोलें दोनों को, right? PDF में 2 PDFs खोलें तो आपको दोनों पेजेस साथ साथ नजर आ जाएंगे. बिल्कुल एक जैसे ही है. छोटे छोटे फर्क हैं और वो आपको मेमोराइज नहीं करने. Concept, if you have understood the concept of the z transform properties and tables, that's it. You already know the Laplace. And like the z transform, remember there was a unilateral z transform also. Zero to. Similarly, we have a unilateral Laplace. We won't go much into detail of that. It does. Bilateral can sometimes have issues with inverse Laplace or z, so often we go for this, but that's a bit more involved topic. We'll skip that. Right, so a few examples. Yeah. What is the Laplace transform? Let's say we want to do a unilateral Laplace transform of delta t. Remember, हमने for discrete time we did pairs of transforms. right? So let's do this and then we finish the lecture for today. By the way, what was the Z transform of delta n? 1, right? Was 1, and region of convergence all Z, yeah, the whole complex plane, yeah, no restriction. What about this guy? Now let's see, I want to find the Laplace of delta t. It won't come as a surprise to you that it's also 1, okay, but let's do it quickly. If I'm applying, it doesn't matter, but I've applied here unilateral, so let's go for that. E minus st dt. This is by definition of the Laplace transform. क्या हो जाएगा ये? E minus st, yeah, that's fine. But what's this whole thing? Let's see, 0 to infinity delta t e minus 0 t dt, sorry, not 0 t, s times 0. Why did I do that?
Because t is 0.
If you remember, we have already discussed that delta t minus t xt is always simply delta t minus t times x at capital T. All the other values don't matter because they will be multiplied by 0. As soon as we do this, what happens to this thing? Becomes independent of time, so it can go out. And what is this value? 1, right? So basically it vanishes. You are left with delta t dt. What is this? 1. The area under this delta t is 1. Sometimes you forget, for this to happen, this range should include the point where it is 0, t is 0, okay? Since it does include that, it's 1. That's the same. What about the region of convergence? What value of s makes this finite? It's not here irrelevant, s, any value of s. So the same conclusion. Yeah? Good. 423. So I'll just quickly write here for unit step and then we can do more later. यूनिट स्टेप का किसी को याद है क्या आया था डिस्क्रीट टाइम में? Z upon z minus 1, yeah. So let's say what is the Laplace of unit step in continuous time. Okay, so 0 to infinity ut e minus st dt, right? Again, what happens to this ut? In discrete, in continuous time, how do we define ut?
1 greater than 0. 0 otherwise.
So what's the range here?
1.
Yeah, in this range it's 1. Yeah, so it's just 1. So what you are left with is e minus st dt. What's the integral of this?
E minus st.
It is e minus st, but something also. And e ax का integral क्या होता है? Yeah, minus 1 over s. इसका जो है 1 over a eax. So you get this back but with a scaling. What's that scaling? Inverse of this guy. So same here. Inverse of this guy, minus 1 by s e minus st, and don't forget the limits, right? So it's a definite integral. So if you put in the limits, it comes out to be 1 over s. Okay. So unit step has integral, Laplace transform 1 over s. Again, you don't have to memorize this, it will be in the table, but you have to be familiar with this thing. I'll leave this as an exercise for you to find what is the Laplace of e minus at multiplied by unit step. Okay, it should come out to be if you try out. Basically, you should already see it by the way. This is what's happening. Yeah, UT ने पहले की तरह गायब हो जाए जैसे आप लोग गायब हो जाते हैं. Industrial visit अगर लाहौर का ना हो, right? अच्छा, then it is only e minus at here. And how can you write this? You can write this as one exponential, right? वो क्या होगा? E, if I'm right, it's e minus s plus a t. ऐसे ही है ना? So then इसका integral क्या होगा? 1 over this scaling time this thing, yeah. So s plus a and 1 minus 1 s plus a, और उसको आप इसकी लिमिट्स डाल देंगे तो you will be left with okay. So what happened when you multiplied ut by e minus at, it changed to from 1 over s to 1 over s plus a. Okay. I will show you similarity with this in Z transform. You have already seen that, but when we come to properties, then we'll see. So next time, I will quickly review properties of the Laplace transform. Okay, it shouldn't come as a surprise that they are actually the same as Z transform. Okay, so we will do that next time, inshallah, and that's yeah, tomorrow I suppose. Let's see. Any questions so far? Something clear? Okay. So to sum up very quickly, what we have done is we have started translating what we learned in great detail for discrete time in both time and frequency. We are now translating that to continuous time in both time and frequency. Okay, and this is what you come to. So after we are done with some more details of Laplace transform, we will go to the final topic of this course, which is Fourier transform. Where does this guy come in now? Yeah, just as a trailer, Fourier is just a special case of Laplace. Okay, why we need that special case? Why is it so popular? Engineering especially, you will hear more of Fourier than Laplace. In mathematics and physics, you hear more of Laplace and Z. There is a reason, we will see next time. What did Z transform do to difference equations? It converted them into simple algebraic equations. What does Laplace transform do to differential equations? You know, it converts them to simple algebraic equations. That's why you use it in circuit 2 and so many other courses. When you are dealing with the integrals, differential equations, you take the Laplace transform, you get a simple algebraic equation, you solve it as you are familiar with how to solve algebraic equations. So this is a complete counterpart of the Z transform. Z will convert difference equations to algebraic. Laplace will convert differential equations to algebraic. And then there is the Fourier, which is special case of Laplace that we will cover later on. Right. Thank you.
Sir, assignment.